Quantum Future Awards. Yes, this year virtual, but the stakes are still very, very high. So here's how that goes. 30 finalists, 30 pre-finalists sent in their ideas. 10 of them became the finalists in 2 categories. The first category, PhD. Second category, master students. All ideas that have been submitted have to do one or the other way with quantum technology, quantum computing, quantum sensing. It's going to be very exciting, and even more exciting it is that we have to award that prize, to award that award. We have gathered a wonderful jury here. First of all, let me welcome Professor Dr. Ina Schieferdecker, German Federal Ministry for Education and Research. So I'm very happy that we at least 2 women here on stage to do that. So that is number 1. And already this morning with us have been the 2 gentlemen who are driving quantum technology, especially in Germany and in Europe. Dr. Markus Krützig, happy to have you back here on stage, and I'm counting on your strong votes. And Dr. Jan Götz, who is, as researcher and entrepreneur, of course, absolutely interested in what is becoming the reality of quantum technology. So, that is the jury, but before we dive into the 10 finalists, Professor Ina Schieferdecker, give them encouragement and good luck, please.
Thanks a lot. Esteemed colleagues, passionate quantum pioneers, honored finalists of this year's Quantum Future Award, ladies and gentlemen. Curiosity, the willingness to engage in action, the courage to explore new paths, and the desire to go beyond the limits of our knowledge every day and anew. These are elementary qualities that are needed to move forward, to be leading edge, to be first, so to say. And quantum technologies are particularly challenging for all of us as cutting-edge technologies. And in order to meet these demands in the best possible way, to keep Germany competitive for the future and to further expand our pioneering role, we launched the Quantum Future program several years ago already. This substantial program consists of a number of measures in schools, university research, as well as in industry. And in addition to the targeted commitment to inspire students with enthusiasm for the field of quantum technologies, the focus of the program is especially on the promotion and networking of our outstanding students, like all of you. As earlier today we said already, we already learned a lot about the activities of the Federal Ministry of Education and Research, as well as of the European Commission in the field of talent promotion. That has been a panel together with Jan and Markus and our Minister Anja Karliczek. And now we are here to celebrate another very important part of the Quantum Future program, and I'm really very pleased to welcome all of you to this final and to welcome the finalists, and at the end to announce the winners of today. Let me say already here at this point, it will be hard to choose, but at the end we need to choose. But this should be an encouragement for all of you, not only for the finalists, everyone who is interested, everyone who was submitting the thesis. Please continue. It's very important that every one of us tries to bring further the understanding of outstanding new technologies and to master the transfer from the research to the applications. And as said before, those 10 finalists for today, they will present in a pitch. We will have the hard job to listen, to decide, and then to the nice job to hand over some of the awards. And you will see that the finalists' work range from very exciting fields in quantum technologies, including machine learning, including the usability or the application of novel quantum effects, or how to construct quantum networks. However, still, the selection does not reflect the broad scope of quantum technology. There, of course, is a lot more. So it also shows that excellent research has found its way into universities, into the master programs, into the PhD programs. And indeed, we see that our finalists come from all regions in Germany. So we have Munich in the south, Hanover in the north, Siegen in the west, or Jena in the east. And we are really happy to see more than, or to see so many excellent universities in our country contributing to advances in quantum technologies. And we are very proud to have students like you, which are at this cutting edge. So, let me finish. So I'm looking forward for your pitches, and I hope that every one of us in the audience has an entertaining time and a lot of surprises and new insights into quantum technologies. And let me say again, thank you all for your engagement, for your contribution, for your commitment, and please continue despite of the jury vote at the end.
Thank you very much, Professor Schieferdecker. That was already a good start into these finals. So my question to you as a jury, are you ready? Do you feel ready as you can be? Good. That is a very second good start, because now we are getting serious. The finals are about to start. Here's how it goes. We start with the PhD students who submitted, and indeed what Ina Schieferdecker said, everything that was submitted was equally broad and deep. So that will make it very, very complicated to choose, but we will manage. In the second part, the second 5 finalists are the master students. Same principle here, deep and broad. Questions in the beginning and for the jury were, of course, how practical is it? How amazing is the research submitted? So whoever is listening to that, maybe you will have the same things to do. And of course, it is a pitch. I'm a communication coach, so I teach people to pitch and present and do things on stage. So do your best, not just in research, but in your pitch as well. Because you only have 3 minutes, not more. After that, we either cut your microphone. That has been done before, even during elections, so be careful. Or I start talking, and actually what I say is not that interesting as what you have to say. So you better be within the 3-minute range, okay? Of course, there is a prize to be awarded. In every category, there is the first prize awarded with 6,000 euros, and the second prize with 4,000. So it's worth all the efforts. Okay, now let's get the finals started. I didn't forget anything. Wonderful, wonderful, wonderful. So my question goes to Andreas Brenhuis. Andreas, you are from Swabia, from North Franconia. You live in Swabia. You published in Nature Nanotech already. And all I know about your pitch, it has to do somehow with diamonds. They play a role in that. Andreas, are you ready for the Quantum Technology Lion's Den? Go for it, you have 3 minutes.
Yes, thank you very much for your kind introduction. Let me start with a brief introduction into the topic. I hope you can see my slide. The progress of the second quantum revolution has laid the foundation to exploit quantum technologies in applications. In the 21st century, this will presumably lead to fundamental transformations in the fields of computing, communication, and sensing. All applications have three technological challenges in common. First of all, one must be able to initialize the quantum system. Secondly, one must be able to manipulate, and finally, to read out the state of the quantum system. In my PhD thesis, I investigated a novel approach to read out the quantum state of nitrogen vacancy centers in diamond. As depicted on the lower left, the NV center is a well-known and understood fluorescent defect in the diamond lattice. Its long spin coherence time, robustness, and room temperature operation meet the demands for an application, for example, in the field of sensing. The state-of-the-art readout concept was based on the so-called optically detected magnetic resonance, where the electron spin resonance is inferred from the fluorescence signal. However, this requires bulky optics and suffers from a low optical collection efficiency. In contrast to this, I investigated a direct electric readout concept, as depicted on the upper right. The idea was to exploit the so-called non-radiative energy transfer process, which is a highly efficient energy transfer process if an emitter like the NV center is brought into close contact with an absorber. To this end, nanodiamonds comprising NV centers have been brought into close contact with graphene. The graphene served as a broadband absorber to read out the excitation and thus the quantum state of the NV center. In time-resolved photocurrent measurements, as depicted on the lower right, I could show that in accordance to the optically detected magnetic resonance, one could observe the electron spin resonance in the photocurrent of the combined signal. The short and long timescale of the detected photocurrent in the picosecond and nanosecond range respectively agree with the distance correlation of the transfer rate of the non-radiative energy transfer process. To sum up, I investigated a novel approach to read out NV centers, namely the direct electric readout of nitrogen vacancy centers in diamond. Thank you very much for your attention.
Thank you very much, dear Andreas. That was within time, and I've seen the jury write and taking a lot of notes. Thank you very much for that. So that brings us immediately to our second finalist. Lucas Fiedere is at the moment, as far as I can see, in Nottingham, but he is from Baden-Baden. Is that correct? Lucas, are you with us?
That's correct, yes.
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 And as far as I can look at this, and the Golden Gate Bridge in the background, as far as I know, in your approach, in your submit, you combine the theory of quantum sensoric with experimental proposals. Are you ready to rumble?
Yes, I'm ready.
3 minutes
Thank you.
to go on this note. Go.
Thank you very much. Dear ladies and gentlemen, the quantum era is here, I want to declare. But is it actually? The first quantum sensors are here, yes, but are they better than conventional sensors? More often than not, the answer is no. But why? Why are we still waiting for strong quantum sensors? Their potential for medical imaging, navigation, and astronomy is huge. We need next generation quantum sensors now. Well, the problem with almost all proposals for quantum enhanced sensors is that they rely on large-scale entangled states. And as a matter of fact, the preparation of such states is extremely difficult. And even if we succeed, they are fragile and sensitive to disturbances. With my PhD thesis, I show a path towards quantum sensors which use only experimental resources which are currently available. And best of all, there's no need to prepare large-scale entangled states. On the other hand, I use insights from theoretical quantum metrology to determine regimes where quantum enhancements are possible. For example, I discover new dynamical regimes of quantum sensors which allow quantum improvements with easy-to-prepare quantum states. Further, I proved bounds on measurement precision which allow us to better understand the true potential of quantum sensors. On the other hand, I use machine learning methods such as reinforcement learning and evolutionary strategies to introduce the new paradigm of smart quantum sensors. Artificial neural networks take the role of a brain of the quantum sensor, which makes adaptive adjustments during the measurement procedure. This makes it possible to utilize the available quantum resources in the most efficient way. At the same time, the precision of such quantum sensors is autonomously optimized. With a detailed computer simulation of the new type of magnetometer, which is subject of a pending patent application, I demonstrate the practical feasibility of these concepts. The quantum era might not be quite here yet, but with my PhD thesis, I paved the way towards a new generation of quantum sensors. Quantum sensors which will be practical, adaptive, and smart. Thank you.
Thank you very much, dear Lucas Fiederer from Nottingham. Thank you for your sensoric approach. Thanks so much. So number 3 in row of the PhD finalists for the 3rd Quantum Future Award is Christian Heider. I hope we see Christian already on the screen. Christian is from Franconia, but at the moment he does his postdoc in Stanford. And last year he graduated there summa cum laude, and now he is pitching options for optoelectronics below a femtosecond. And that means he knows everything about timing. Christian, are you ready to use your 3 minutes impactful?
Yes, I'm ready. Thank you.
Okie dokie, then go.
So, dear series, thank you very much for this opportunity to present at this fascinating final. So, I will show you that we can control and manipulate qubits in graphene using novel light sources. So, here is the basic. So, when we describe an electron in a band structure, usually we associate an electron to some certain energy state. So you see that the electron is here in the energetic lower state. And when the light interacts with this electron, what we can do is we can bring this electron into a superposition state. So now you see the electron has a probability to be in one or the other band. And such a state is known as qubit. And this is relevant for quantum technology. However, one problem on this qubit is that the lifetime is usually very short. So this is why you cool down the system. Another way what you can do is you can try to control it very fast. And the fastest control tool what we have is a light. So what we use a light field to control the qubit. So in a sense, what you can think about is what we do is we have an electron with some binary information. It can be 0 or 1, depending on which state it is. And then we bring it into a qubit, and this qubit is a kind of quantum mechanical state. So it contains way more information. It's like a wave. So you see a wave has some amplitude, which tells you where the electron is, but also quantum mechanical phase. So way more information. And after the laser pulse is gone, we can imprint this back to some kind of binary information. So in a sense, what we do here is we imprint information from light to the electron at very fast timescales. So that's very interesting to think about it, but actually even more interesting is to do this in the lab. And we can do it. We have graphene on top of another material, and we can control and manipulate the qubits in graphene. And one thing what we also need is a readout process. And to make an electronic device, we have an interface to another material. And we could show that the charge transfer is as fast as 0.3 femtosecond, which actually is the fastest charge transfer time what we have at the moment. And this we can use to read out this information which we imprinted from the light to the qubit. And such a chip I've showed you initially at the beginning is actually very simple. We can do everything at room temperature because we do it fast. And the chip, we have some electrode contacts, which you see here to read out in principle the information. And when we do the measurement, I mean, with novel photonic sources, we can change the waveform. So we imprint information to the qubit, and this we can do very fast. So here you see the measurement on the x-axis, you see the time scale of femtoseconds, and we can turn on off the current. So we imprint information to the current, and we can really measure it. And by doing this, we can now really bridge the photonics with electronics towards novel quantum technology, which will be certainly for future application. Yeah, with this, I want to thank you for your attention.
I'm absolutely impressed that you are not just submitted absolutely interesting stuff, but stayed in presentation time. To me, as a communication coach, that is absolutely perfect. Thank you very much. And we do have another Christian as a fourth participant in the PhD round, and that is Christian Pilz. Christian is from the Waterkant, from Hamburg, and he is already working in the laser optic industry. He already published in Nature Communication articles, and he pitches today to quantum computing via ionic states. Christian, are you ready to let the qubits fly? Then
Yes,
go
I'm ready.
in 3 minutes.
Thank you. So a quantum computer that combines the concepts of digital data processing with quantum physics would allow us to tackle important computational problems decisively more effectively than any classical computer. So using quantum computers, we could gain unprecedented insight into different research fields also far beyond physics. And some possible applications are a better understanding of certain biochemical reactions. So the developing of a vaccine against a virus has some relevance in these days, but also the development of more powerful batteries for electromobility, machine learning, artificial intelligence, optimizing logistics or traffic in modern cities, and many more applications could also benefit from quantum computers. And the two frontrunners in the quest for scalable quantum computers today are superconducting qubits and trapped atomic ions. And I will focus on trapped atomic ions. So each individual ion acts as a quantum bit supplied by nature itself that stores and processes information. And laser light is typically used to control these quantum bits. However, the use of laser light comes along with both technical and fundamental obstacles when scaling the trapped ion concept up to a large number of quantum bits. Therefore, instead of using laser light, microwave pulses, a technology that is already inside your cell phones available, may help to overcome these hurdles. Now the question is, can we build a prototype quantum computer based on atomic ions and already accessible microwave technology? And this is the topic of my thesis. And one seeming obstacle when using microwave pulses is the fact that they cannot be directed to a single ion only, which makes single quantum bit control impossible. In addition, microwave pulses cannot make the ions interact with each other, which prevents any possible or any necessary and useful data processing. However, placing magnets close to the ions can solve these challenges. And my colleagues and I could demonstrate the control of individual quantum bits with microwave pulses with high accuracy without affecting other quantum bits. We also demonstrated that we can effectively turn on and off interactions among certain quantum bits simply by applying microwave pulses. And this allows us to use selected atomic ions either as a processor that processes quantum information or as a quantum memory that keeps the information stored. And most of the developed methods are quite general and may be adapted to other quantum computer hardware platforms as well. So having all these ingredients, the control of single individual quantum bits and their interactions, we even could run a reasonable quantum algorithm. And with further technical improvements and already having a blueprint at hand, my work may hopefully help paving the way to an ion and microwave-based large-scale quantum computer that may improve the quality of all our lives and our environment. Thanks for your attention.
Thank you. And if you win or not, this is already a very fascinating idea that, of course, should be pursued. Winning or not, it's worth it. Thank you very much, Christian. Last in the PhD row is Hartmut Michael Zopf. Hartmut is from Saxony, from Dresden. He works now in Hanover. I'm from there too. I wonder why this happened. Anyway, now you do your doc in Hanover and you published already in Nature Communication. And now, today, in your pitch, you talk about how quantum points can become quantum repeaters. Hartmut, are you ready for action? 3 minutes.
Yes, sir.
Go.
Yes, thank you very much. So let me show you what I did during my PhD studies. So I worked on semiconductor-generated entangled photons, and semiconductor materials are, of course, very interesting since they are embedded in most of the electronic devices we know today. But for the so-called second quantum revolution, semiconductor devices or materials are not so strongly involved yet. And this is something that I looked at during my PhD studies. Together with my colleagues, I developed a gallium arsenide quantum dot-based device, which solved several problems that the scientific community had at the time. First of all, we demonstrated a record entanglement fidelity of 94% between these two entangled photons that this device emits. Additionally, we found a clever way to extract the photons to a very high extent of 65%. And we also looked into the coupling with quantum memories by tuning the wavelength of these quantum dot light sources in order to couple them to rubidium atoms. Now, what can we do with such a device? The idea is to bring this to application in quantum networks. And if you're talking about quantum networks, then the quantum repeater is a critical component that you cannot get around. The so-called entanglement swapping scheme lies at the core of a quantum repeater, which allows for the extension of large-scale quantum networks. And this works like this. So initially we have two entangled photon pairs. So the blue and the red photon are entangled with each other. And then if we take these two red photons and send them to a so-called Bell state measurement, and if this is successful, then we will have teleported the entanglement from the initial pairs to these blue outer pairs. So the blue photons are now entangled with each other. Now we thought, okay, with this device, we really want to try if this also works. And we were able to, for the first time, demonstrate an entanglement swapping with semiconductor material. And this can be very nicely seen in the two photon density matrix shown here. So in the top, you see the real part, and at the bottom, you see the imaginary part of this matrix. And if we had a perfect entangled state, then these inner columns, they should be at a value of 0.5. And you see, we can get really close to that, and we extract an entanglement fidelity of 81%. And we were able to publish these results in Nature Communications and Physical Review Letters. And with this, I would like to thank you all for looking at my talk. Thank you.
Thank you very much to Hanover. Fine, thank you. This is the end of the PhD category, and I want to encourage you, all of you who are watching this live or later on in the stream, if you think this is something for me, if you think this is something I'm interested in or I can contribute, even if you're not a quantum physicist, it's probably worth sending in a contribution, because next year there is going to be an award like this, the fourth one. I very much hope so. So I want to check back with you as a jury. That was quite a ride. Yeah, right? So how are you feeling up to now? Is it thrilling? Is it going to be close? I'm just curious.
Well, I think we're all impressed by the quality of the work and, you know, the high density. So we all made notes, I guess, a lot. And so it's not going to be easy. No. So, I mean, this was really, really fascinating.
Yeah, yeah.
Well, yeah, nothing to add. So I don't know yet how the decision gonna go. So thank you very much for these interesting insights. And 3 minutes are by far
it's tough, right?
Too small time.
Right, and they did all very well in doing this. So I think it's an important thing. Jan, did you find some Heiders already?
Well, at least, well, it's going to be a tough decision on who wins, but actually I already made some notes on ideas on maybe how we could combine some of their ideas with it.
Because it's not just about winning itself, it's about participating, and it's about contributing and collaborating. In the panel this noon, this was one of the most important points, that working between industries, between branches, interrelated. That is going to be the future of quantum technology, quantum physics, not just physicists, but maybe linguists, I don't know, maybe culturalists, biologists, chemists. It's all a very fascinating group of people, engineers anyway. So we switch in mode from PhD to master, and I see already our first candidate in the background, and there's a very old-fashioned school board in the background. That's going to be very fascinating. Warm welcome to Paul Fehrmann. It's a home run for you. You're in Berlin, you're from Berlin, and you optimize the algorithmic runtime for noisy and noise-corrected quantum computers. Paul, please make some noise, but only in 3 minutes.
Thank you so much. So the goal of many quantum computing scientists like myself is to use fully fledged quantum computers to simulate molecules and proteins, invert matrices, and factor numbers. To give a perspective, factoring a 2048-bit number requires about 20 million qubits and runs for about 8 hours. On the other hand, we currently have more like 100 qubits that survive for less than a minute or even seconds. Nevertheless, almost exactly 1 year ago, Google showed that even with these faulty devices, you can still outperform classical machines, thereby achieving the important milestone of demonstrating a quantum computational advantage. However, the problems they currently solve are completely useless except for the generation of provably random numbers. It is therefore one of my goals to look at algorithms and problems that can be used and run on these noisy devices that are still of practical use. A great contender here is the framework of parameterized quantum circuits, which you use to run hybrid quantum classical optimization methods. Here, you have a fixed circuit with parameterized gates, and in the end, you perform some measurements to construct a problem-specific loss function. You then use a classical optimization loop to optimize the parameters of these gates and minimize this function. This looks very much like a classical neural network, but a main caveat here is that since nature is quantum and this is a quantum device, you can't use straightforwardly any kind of backpropagation in this case. Nevertheless, we showed that if you take a look at it and realize that since quantum mechanics is probabilistic, you can try use a stochastic gradient update. And we showed that this actually works for some examples, and that even just performing single measurements per gradient update is sufficient to converge and to reach solutions, thereby greatly reducing the resource cost of running such algorithms. That these tasks and that the setup is actually useful and our methods are of great value is stressed by the fact that even shortly after publication, our results were incorporated into PennyLane and TensorFlow Quantum. Both are frameworks we use to simulate and program quantum computers. And that this happened so fast is really exciting for me. Now, the next step in achieving this goal is to look at specific problems you can run on these devices that also build this architecture in such a way that is suited to current devices, and also look at different update methods like natural gradients or quantum natural gradients. These goals I am currently pursuing as a PhD student with Professor Jens Eisert here in Berlin. Right, and to summarize up, this thesis helped pave the way to achieve the next milestone that is that quantum computing is still lacking, demonstrating a practical and usable quantum advantage. Thank you so much.
Thank you very much. Thank you very much, Paul Fehrmann, as being the first in the master students group. Thank you very much for this. And the school board, I'm very impressed by the school board in the background, which has nothing to do with the quantum technology, but explains a lot of things more easily. Next in line is a lady, and I'm very pleased to see that we have a couple of ladies in this master student panel, in this award panel. And next one is Eva Grossman, and Eva is from Swabia as well. She studied physics and pitches here about microwave structures for coherent control of nitrogen vacancy centers in diamonds. And as we all know, diamonds are girls' best friend. Eva, that sounds like fun. Tell us more, but only in 3 minutes.
Yeah, thanks for the nice introduction. And yeah, as already said, my thesis works with microwave structures for coherent control of nitrogen vacancy centers in diamond. One ongoing challenge in life and physical science is sensing weak magnetic fields. A promising measurement system is the nitrogen vacancy center, as we already heard today. And the nitrogen vacancy center consists out of a vacancy and a neighboring substitutional nitrogen atom in the diamond lattice. It offers the possibility of an optical readout of its electron spin state, and as well as spin manipulation via microwave fields. It also has an extraordinary high magnetic sensitivity, which allows or enables a structural analysis of molecules on the nanoscale. The sensitivity can further be improved if we increase the number of used nitrogen vacancy centers in our experiments. If we perform experiments with single nitrogen vacancy centers, it's relatively simple to apply microwave radiation, as we only span a simple wire over the diamond and just apply our microwave radiation. But if we want to coherently control a large number of nitrogen vacancy centers, we need special or adapted microwave mediators. So my thesis in general focuses on the creation of such new microwave structures. And first, by simulating these structures, then fabricating and subsequently benchmarking such new structures, we obtained an optimized omega-shaped structure. And this new structure allows us to coherently control these nitrogen vacancy centers within an area of about 0.23 millimeters squared. This fact, or with these microwave structures, we get a very enhanced magnetic sensitivity, which can be further measured in experiments. So I want to thank for the attention, and good luck for the other contestants.
Thank you. Thank you very much. Thank you very much, Eva. I'm very happy that many people who submitted an idea here came from many different areas. And our next candidate in the master category is a Swiss import, grew up in Bavaria and lives now in Stuttgart. So she has a master in photonic engineering and is working already as a development engineer. Luisa Hopper, are you ready to make a flash impact in the next 3 minutes?
I am, thank you. Okay, so hello again, I'm Luisa Hopper. I did my thesis at IFSW in Stuttgart together with the company of Quant. During my master thesis, I've developed an industrial process for the fabrication of high quality, reproducible, nonlinear optical waveguides. Because I think, of course, it's really important for quantum technology, but how do I actually get to such a conclusion? Everyone here today is really excited about quantum technology and its industrialization. All the other contestants already presented some really interesting and fascinating new developments in quantum sensing, quantum communication, and computing. But one remaining important challenge in almost every development is that rapid success is often hard to achieve because the availability of appropriate enabling components to actually realize a device is often not given. For example, the scalability of quantum computers is still a problem, where an important component is the quantum photonic integrated circuit, which you can see on the left in the slide. I want to remain a little bit in this example. The central component in the quantum photonic integrated circuit is the nonlinear waveguide, which is used for entangling quantum states. So a possible solution is now a fast and reliable production process for such components, which I did in my thesis about femtosecond laser writing of low-loss waveguides for quantum applications. The approach was a sequence of simulation, fabrication, and optical characterization tests. And the actual key was the optimization of laser and design parameters of an ultra-short pulse laser system for the ablation of the nonlinear optical material, which was lithium niobate in my case. My major result was an ultra smooth surface roughness and thus good surface quality of my waveguides, which is shown in the right on the slide. This enables super low losses of the waveguides, and the thesis finished a year ago. Back then, I was able to set new benchmark values of 2.2 decibel per centimeter loss for visible red light, which was back then already half of the previous literature result. back then. Now we even got better. It's easy to reach values below 1 decibel per centimeter. As a resume, a basic technology for rapid prototyping of waveguides and waveguide devices was demonstrated, and the quality of femtosecond laser writing in lithium niobate was improved with respect to losses and surface roughness. As a perspective, I will continue to work on this project. Thanks.
That continuation is always a good idea. Thank you very much, Luisa. Thank you. Thank you. Number 4 in row is Ashwin Rajagopalam. Of course, I said that there is many different cultures coming. I'm very happy. He comes from Chennai and he works in Hanover now on his doctor's thesis. So he comes from the warm continent, subcontinent to rainy Germany. And he's working on optimizing hybrid inertial sensors. Good luck, Ashwin. Nala Atirstam for the next 3 minutes to you.
Yes, thank you. Thank you for the introduction. So the concept of my thesis is to combine an atom interferometer with an optomechanical resonator and have a hybridized quantum sensor, which is suitable for high inertial noise environments. So the atom interferometer can perform precise measurements of inertial effects with high long-term stability, but suffers from cyclic measurements and dead times. Whereas the classical sensor in comparison can measure continuous signals, but it suffers from long-term drifts. Therefore, by combining the two sensors, we have a hybridized sensor which possesses the complementary benefits of both the devices. So here we see a space-time diagram of an atom interferometer. So in order to perform interferometry, we allow the free fall of a cold ensemble of rubidium atoms along the direction of gravity. During free fall, we integrate the atom cloud with counterpropagating laser pulses with a fixed time duration between them. The interferometer measures acceleration with respect to the inertial reference mirror. The output response of the interferometer is a normalized atom population, which is measured at a specific internal state of the atoms. In laboratory environments, we isolate the inertial reference mirror from ground vibration, but with compact transportable devices, in the absence of vibration isolation, ground vibration basically couples in through the inertial reference mirror and distorts the phase of the interferometer and therefore hindering its sensitivity. Therefore, by combining a classical inertial sensor along with the inertial reference mirror, the interferometer fringes can be restored and its sensitivity and dynamic range of the atom interferometer can be enhanced. We have used a novel optomechanical resonator in order to suppress vibrational noise in our atom interferometer. So the optomechanical resonator is monolithically made of fused silica, and it comprises of a harmonic oscillator with a test mass. The test mass displacement is basically measured with an incorporated Fabry-Perot cavity, and the acting acceleration is inferred from the test mass displacement. The optomechanical resonator has several advantages over commercial accelerometers, starting from compact dimensions to customizability. And so with such a hybridized device, it is highly suitable for measurements in high inertial noise dynamic environments. And with the use of a compact optomechanical resonator, there's the potential of miniaturization of the atom interferometer sensor head. And finally, such hybrid devices can be used or has the potential to be used in inertial navigation and on-field gravimetry. Finally, my thesis has followed on to become a publication, and it has been accepted in communication physics. With this, I'd like to thank you for your attention.
Thank you very much. Thank you very much, Ashwin. That was wonderful. Last but not least, from Barcelona to one of the optical hotspots in Europe is Adria Sensaperna, who is working there at the as a research assistant at the Fraunhofer's Institute for Applied Optics. Jena, as I said, is one of the hotspots for the optical industry in Germany and the whole world. So Adria, are you ready to let the photons dance for the next 3 minutes? Go for it.
I'm ready. So, one moment. Yeah, I hope you can see my screen now. So, I will now talk a little bit about my master thesis, which was in the development of a new quantum entanglement wavelength suitable for microscopy and cryptography. So first of all, entanglement is a phenomenon of quantum mechanics that was first derived theoretically, but it's actually very interesting because it has also brought some applications into our real world. For example, in quantum cryptography, which is very linked to the development of quantum computers, but also in quantum microscopy. So in the case of quantum microscopy, quantum entanglement of photons can be used to generate a better image with a microscope than classical light. And in this sense, there's a European project called QMIC, which aims at the creation of a new kind of microscope that will use entangled light as its source of illumination. And in Fraunhofer IOF, I was responsible for the development of a new kind of entangled photon source for this microscope. So the challenge here was that most sources of entangled photons generate photons in the near infrared, but most microscopes work with visible light. So I had to, for the first time, generate an entangled photon source that also generated photons in the visible light. And in this case, it was about 500 nanometers, while also keeping in mind the interoperability and usability of the source. So to do this, I had to look at the schemes available for the production of entangled photons. And then I tried some number of schemes. So I built in the laboratory 4 different schemes. And I tested, for example, a new crystal that is under development and some scheme to generate entangled photon sources that is designed to be used in satellites until I finally could produce entangled photon source for the first time in the lab at this new wavelength. And this actually happened with the more simple scheme that I tried was the one that worked the best finally. So this was a check mark that I could generate the entangled photon source for the use in the QMIC microscope. And now naturally the next steps is to integrate my entangled photon source with the rest of the microscope, which is in Barcelona. And also in Fraunhofer IOF, we have envisioned to compactify even further the entangled photon source that I've made and use it as an enhanced illumination add-on for microscopes, so that my entangled photon source could be already used with existing microscopes by connecting it and using it as source of illumination to then receive directly and in short term the advantage of using entangled light. And this is everything from my side. And I want to thank you for allowing me to talk here today, and also thank the rest of the speakers for their interesting contributions.
Congratulations to all the finalists. Well done, really, really well done. I don't know how about you, but I found it equally inspiring and tough. It's very intense, right? To follow everything and then to say like, oh my God, what do I do now? So, but luckily, I do not have to take that decision. It is up to you to gather and discuss all the submittants, as well from the PhD side as from the master side. This is your task. Now the audience on this side can relax a little bit because I have the pleasure to introduce for the next couple of minutes a very special guest. Sabrina Patsch is a physicist as well, but she also is a science slammer. You know science slammers, these are the girls and boys, the ladies and gentlemen that kind of translate science in its phases, its complicatedness, into something really appealing to us as an audience and make us wow and aha and think like, oh yeah, I've never seen the world like this. It could be something I should pursue as well. So what hooked me especially, she thinks that the universe tastes like raspberry. And even if her Science Slam today is not about astrophysics, I found that a very fascinating thing and hope she can dive in together with you into the wonderful world of science slamming and translating science into the real world. Thank you for having her here. Sabrina Patsch.
Thank you. So I can only guess how you must feel now, right now in front of your screens, being excited about who's the winner of this award. But there's not really much you can do right now. So try to lean back and relax for a few minutes, because it's really out of your control. And I understand that this is quite a hard thing to do, because I have to admit, I'm quite of a control freak myself. And for me, the problem really is I cannot accept if people do something in a non-optimal way. And to give you an example for that, imagine little me in kindergarten, and one afternoon we were supposed to play with finger paint and paint the wall. And while all the other kids were happily playing, I was sitting there and I didn't understand why did they make us do that? Why did they make us paint the wall with our hands? Couldn't they just give us one of these grown-up stick things with a paint roll in the end? That would be so much faster, and I could be sleeping already. But yeah, I had to learn how to live with my control obsession. And I did not only learn to live with that, I also managed to make it my career. And all of that started in the last year of high school, when I had to think about what do I want to do with my life. And back then I had two different options. One of them was I was playing electric guitar in a rock band, and I don't want to brag, but we had 2 concerts already. So I think the next breakthrough was probably not very far away. So naturally my first career option was a rock star. And I thought maybe I also need a plan B, so I thought, I also like physics quite a bit. And then in the last year of high school, I also learned about quantum mechanics for the first time, and more specifically about the experiment of Schrödinger's cat. And there was this experiment where physicists took a cat and a bit of poison and put it in like a cardboard box, and then they managed to bring the cat in this wicked zombie state between dead and alive. And I found this so fascinating, and I thought, this is control. This is what I want to do. And therefore I decided I don't want to become a rock star, I want to become a quantum physicist. And therefore I started studying physics, and I learned quite quickly that I, as a control freak, am not very alone there. But this old picture of scientists sitting under trees, looking into the sky and thinking about nature is not really up to date anymore. But what's more the reality is this picture of the maniac scientist trying to rule the world and control the world. And therefore I felt quite comfortable there, I have to say. And there was one discipline which I liked a lot, and that was quantum technology, because I think they really mastered the control. But I have to be a bit more specific here, because there's the so-called first and second quantum revolution. The first quantum revolution started in the 20th century. And there, scientists were still taking the nature as it was given to us. So they were just taking what we had to build new technologies. For instance, the GPS, the laser, semiconductor science, which is used nowadays in smartphones and laptops everywhere. But all of them have in common that we use our new understanding of the world that quantum mechanics gave to us to build these new technologies from these basic building blocks. But it can also be a bit better, and that happened in the second quantum revolution. And here, scientists didn't accept anymore how the world was going, but we wanted to control the world, and we wanted the world to play according to our rules. And one very famous example for that is, of course, the quantum computer. But there's also different quantum technologies that are honestly not very well discussed outside of science. Nobody really cares about them. But they all have one thing in common, and that is that we want to shape nature. We want to bring it in highly unnatural states with which we can now then build the new quantum technologies. And I decided to stay in this field, and I also discovered that there's one royal discipline of control. And this is called OCT. So it's called optimal control theory. And here everything is really about making atoms dance to our tune. And you can already see this is the perfect discipline for me, because I could combine my love for music with my being a control freak. And in the following I want to explain you a little bit how I'm actually doing that and what I'm doing to the atoms. So let's start looking at an atom in its ground state. You see here in the middle there's the atomic core, which is quite sleepy. And outside this blue bubble, this is the electronic distribution. We call this orbital. And this ground state atom is quite boring. So now let's excite it. We want to make the atom dance. And this in the background now is the so-called F orbital. We call it the Fiesta orbital. And the question is, how can we make the atom dance? Well, nothing easier than that. We just play music. I think that works quite well, and it's also quite easy, so everybody can do that. But there's a problem with the Fiesta orbital, and that is, as you might know from parties, every wild dancer can spontaneously just fall asleep again. And this also happens to our Fiesta orbitals. And therefore, we want something more stable to make it usable in quantum technologies. And I was looking at this state here. And here we have something like a ballerina state. So we want the atom to spin around its axis. And as a result, the electron is then turning around the waist of the atom like a hula hoop. And this state is now much more stable than the Fiesta state. Because, well, ballerinas are quite robust. So if you ever try to punch a ballerina, I wouldn't recommend that. But the question that we have now is still, how do we do that? How do we bring this Fiesta atom to turn around its own axis? And that was the question that I was asking myself. And for this, I was using a method which is very used in physics, but not many people admit it. And that is, I was guessing. So I just thought, which melody would I play? And I tried this one. I think it already wants you to turn. But so we're a bit closer to what we had before, but we're not quite there yet. And in order to make this melody now better, I was using optimal control theory. And in this one, we are taking the melody and change single notes to see what's happening and to try to improve our melody. And this already works a little bit better, so the blue bubble became a little bit smaller, but we're not there yet, so let's do it again. Yeah, so I think we're on the right track here, but we have to repeat this several times now, and I spare you the details and spare you the next, let's say, 173 iterations of that, and I directly show you the result. I think that's a very neat melody. And for me, as a theoretical physicist, I would say the problem is solved. We found the melody that makes our atom turn. But unfortunately, the story is not over yet. Because it's not quite enough as me, as a theoretical physicist, if I find the melody that makes the atom turn and write it down on my computer or on my sheet. But I also need the people who play the music, and that is the experimental physicist. And if I now take this melody and give it to the experimental physicist, well, they will call me crazy and say that nobody could ever possibly play this melody. And I have to say they're right, because to be honest, they tried, and it sounds a bit like that. And I think no atom would like to spin around due to this music. So the experimentalists were annoyed, I was annoyed, and nothing worked. But I have to say I had another brilliant idea, which is a bit of a more unorthodox method in physics. And this was, I talked to the experimentalists. So I went to the laboratory and I asked them, well, how fast can you play? How high can you play? What is keys? How do I hold a violin? And they explained me all of that. And then I did this optimization of the melody once more. And then the result was a much nicer melody. And you see, it looks much better and it does what we want it to do, but it sounds much more pretty. So we're almost there, but of course I have to tell you, we did not play music to the atoms. But what we did in the end, we used radio frequency pulses, so electromagnetic radiation with a specific frequency. And the experimentalists were, of course, not playing violin, but they had electrodes in their experiments. And then what I did is, I didn't write sheet music, but I wrote the shape of the voltages that the experimentalists had to apply to the electrodes. And I want to give you a short picture of how that looks now. So this is the first melody that we had. And this one was quite simple. And you see the pulse is a dream of every experimental physicist. It goes on, it stays constant, and it goes down again. Easy. Then the second melody is a bit more complicated. So if you look at the axis, you can see it's actually 50 times higher and 10 times faster than before. And no experimentalist can produce that anymore. But the last melody that we had, That is much nicer. And here you see it's kind of a mixture between the first two pulses, because in the end it's quite easy and simple, but in the beginning we have these variations. So this works very well. And with that one, the experimentalists are happy, I am happy, the atom spins, and we're at the end of the story. And this was how I could use optimal control theory to make my control obsession my profession, and to make the atoms dance to my tune, and in the end prepare robust states which can then be used to come quantum technology a little bit closer. Thank you.
So it's hard to applaud nowadays on stage. Thank you very much. Thank you very much, Sabrina, for explaining music and being a control freak. I think that talks to a lot of people, and maybe all the control freaks become quantum physicists.
I hope so. I hope so.
Thank you very much, Sabrina Fadj. Merci. So you are back, and you are still alive. That's a good sign for me. So that is good. Nobody was hurt.
We won't comment.
Very good. Did you come to a decision? Did you come to a conclusion? Do we have winners? Do we have second places? Yes. That is good. So let's start, of course, with 2 times 4,000 euros to be awarded for the second place for PhD category and master category. Jan, we agreed that you are presenting the second place in the PhD category. Drums, please. Who came in second in the PhD category?
Yeah, so first let me say it was really not easy, and we had actually a quite good discussion, and these were all excellent PhD theses. And I'm actually personally happy that I can announce the second place, because it goes very much into the direction also what I have been doing during my PhD thesis with a different technology, but still similar content, and also what we are doing now in our company. So the second place in the PhD thesis goes to Christian Pilz for his work on quantum computers, where he has been using ion-trapped quantum computers to do Fourier transforms. And actually what I also again like is that there were microwaves involved in this technology, which I kind of have been dealing with all of my life. So actually here we see nicely how also the different techniques to do quantum computing can interface in the future. And also it was very application oriented, so there was a real application done in the thesis. And this made us conclude that the second place for the PhD Quantum Future Award goes to Christian Pilz.
Christian, congratulations. Are you happy? Are you happy?
Yes.
Yeah?
Yes, I'm very happy.
Good.
Thanks a lot.
That is good to know. Thank you very much for being happy. 4,000 euro for a study journey, wherever that might take you, whenever it's going to be possible again. Congratulations again. So the second category, of course, second place with the masters. The master students, not that experienced, probably, as a PhD were. You work with them quite a lot in your daily work. You've been doing that the last week. Did you have a second place?
We do have a second place.
Very
and
good.
With a second place, we would like to acknowledge that you also need to have enabling technologies as building blocks for future devices, especially if these enabling technologies can be manufactured in a scalable way. And so I'm happy to announce the second winner of the Quantum Future Award in the Masters category to Luisa Hopper.
Luisa, is that beautiful or is that beautiful? Congratulations to you. 4,000 euro for a study journey, wherever it will take you, whenever it's going to be possible. Is there anything in particular that impressed you with all these submittants, and especially with Luisa's ones?
Oh, definitely. I mean, the quality of all of the master theses have been very high. You see it in structure, you see it in scientific value, but you also see the application. Yeah, you see why we need to study and work on these things and what they can be used in the future. And that impressed me a lot.
Yeah, cool. So, Professor Stiefedecker, now the burden is on your shoulders. We have 2 first places in the master category, in the PhD category, each of them awarded with 6,000 euros for something research-oriented, and maybe a bottle of champagne next to it. Maybe just one.
Yeah.
Do you have winners for us?
So
please start with the PhD category.
Of course, the burden has been on the students and on their supervisors, and we are happy to have received all these interesting submissions and master and PhD theses. I had great jury here to finally decide. Of course, it took quite a long time before to analyze your thesis and to vary the advantages and to put them into relation. And I'm very happy and honored to present. We start with the master?
With the PhD, please.
You want to have the PhD first? Okay. Then to give the first prize for the Quantum Future Award this year to Markus Zopf on for his PhD on semiconductor-generated entangled photons for hybrid quantum networks. And so congrats to you. And of course, I'm happy to announce this award to you because I'm telecommunication engineer, I could say. So I work long time on communication networks, and it's interesting to see how quantum technologies will finally also help us to develop the quantum internet, and that's a very interesting contribution, very important. So, as I said before, please all continue, but also look into the next steps to build up the network. And maybe I can also give a short link to the QNet ongoing project, where we hopefully gonna have first demonstrator experimental results and demonstrators end of this year, and maybe you find your way into this QNet project as well.
That would
Congrats.
be more, but is it maybe better than the prize, right? Congratulations. Are you happy, or how happy are you?
Of course, yes, I'm super happy. It's really a privilege to be here and to win this prize. So thank you so much.
There is one prize left, one more 6,000 euros for a master student. So.
Yes. And the last award that we are able to hand over today goes to Paul. So, and with his last name, of course, there's certain sound linkage to Fehrmann, so maybe that has been your plan all the time. And now I could say, as mathematician, I'm very happy to see that a more theoretical results makes the first place, and in particular a result that helps us to find a way to the needed algorithm for the quantum computers. So very, very important. And indeed, with our projects, once again, to give a linkage, we have, so to say, the line of developing algorithms and to think about the needed software stacks so that the physical systems can work or come together with the algorithms and the software at the end. So congrats, and well, very interesting presentation, difference. You made us really listen well, and congrats for your written thesis as well. And please continue.
Can we have some words from the winner, please?
Yeah, thank you very much. I'm really thrilled, and also thrilled to be here. And it happens a lot that people dig their heads into their own research, so it was really nice to see so many interesting pitches from the other finalists and see what's going on there on exciting projects on these type of technologies. And thank you so much.
Congratulations to you. It's been really, really wonderful to listen to all these contributions in this final. Thank you very much for you as a jury, Markus Kritzig, Professor Ina Schiefer-Decker, Jan Götz, for your contribution to that, for your brains to comment on all these finalists. So it has been 2 categories. It has been 10 finalists. 5 PhD, 5 masters. Now, if you want to be in this hot stuff next year, start now. Busy yourself with quantum physics, quantum technology, quantum sensors, or if you're an engineer, maybe you have an interesting subject where you say, hey, that might be interesting for somebody who is already working in quantum technology to talk to. Now's the time. Next year, there probably will be an award ceremony for this year's award, a real one, the shake hands and all that, we hope so. And of course, there will be already the fourth one. So if you want to be part of that, now's the time to start. Thank you very much for joining us today on the screens or here live. Have a good time, stay healthy, and good luck to all quantum technology ideas. Let's pave the quantum way. Thank you very much.